Hello everyone, so let's look at how we can use equilibrium constants to calculate the equilibrium concentrations of different species for a certain equilibrium reaction. So we're told that carbonyl bromide decomposes to carbon monoxide and bromine according to the following equilibrium. And we're also given that Kc for this equilibria is 0.19 at 73 degrees Celsius. We're then told that you place 0.05 mole of carbonyl bromide in a 2-liter tank and you heat it to 73 degrees Celsius. And you're asked then, what are the equilibrium concentrations of carbonyl bromide, carbon monoxide, and bromine? You also asked what percentage of the original carbonyl bromide decomposes at this temperature. So let's first determine what are the equilibrium concentrations, and then from that we will be able to determine what percentage of the original carbonyl bromide decomposes at that temperature. So I've written down the initial concentrations for us. So that is, of course, we're given the number of mole of carbonyl bromide that you place in the flask, and that gives you the initial concentration of it. And there is none of the products that you are given. So you don't start with any of the products, you only start with the reactant, carbonyl bromide, and that gives you a concentration of 0.0250 because you have a number of mole in 2 liter, and you can calculate the concentration from that. So then to calculate the concentrations at equilibria, we can use an ICE table. So remember, ICE table is just to summarize the information. It's not like a formal method or something special. It's basically just a way for you to keep track of everything. So initially we know that we have 0.0250 molar of carbonyl bromide, and we have 0 molar of each of carbon monoxide and bromide. Alright, so that's of course molar, so I've indicated that here on the left hand side, so we're working in molar. So if you just want to write ICE, just remember to indicate what units you're working with. These tables, of course, are actually just mass balance tables, so they can in principle work with number of mole as well, but because the Kc works in concentration, we work in concentration. Alright, so our next step is to determine what is the change. So initially we have a certain concentrations. Our next step is to determine whether or not the reactant concentration needs to decrease or increase, and the product concentrations need to increase or decrease. And of course the parameter that tells us whether or not or what needs to happen is the reaction quotient. So let's go ahead and calculate the reaction quotient. So for this reaction, so that's bromide, carbon monoxide, so hopefully you're able to write that by now. Okay, and plugging in these initial concentrations, we see it's 0, 0, and divided by 0.0250. Okay, and that gives us a value of 0. So that means the reaction quotient, well, I mean, it's not shocking. We just placed the reactant in the flask. We didn't place anything else. And that makes sense. So comparing that to Kc, we see that that is less than Kc. Kc is equal to 0.190. So making it less than Kc, that means that our forward reaction is favored. Alright, and because the forward reaction is favored, that means that our reactant concentration must decrease to reach equilibrium, and our product concentrations must increase to reach equilibrium. Alright, and we indicate that by that the reactant concentrations must decrease, our product concentrations must increase. Alright, so this whole thing that we did there gives us information regarding the change rho in our ICE table. We also know the amount that this needs to change by. We always designate that by an amount x. And then we need to look at if there's any stoichiometry that we need to take into account. And we see that this is a 1-to-1-to-1 reaction. So in other words, it's just minus x plus x plus x. Okay, so there's nothing else to take into consideration here. So that means then at equilibrium, it's 0.0250 minus x, 0 plus x, that means there will be x carbon monoxide, and the same for bromide, there will be x of it at equilibrium. All right. So now the question is, how do we determine this amount x? And that is where we turn to the equilibrium constant. So we can use the equilibrium constant, Kc, which is equal to 0.190. And we can use its expression. So bromide, equilibrium concentration, carbon monoxide's equilibrium concentration, divided by COBr2 at equilibrium. And these are, of course, equal to these rows here, because let's maybe do this in a different color. So this here, this is the COBr2 concentration at equilibrium. This is the CO concentration at equilibrium. And this is the Br concentration at equilibrium. So we can go ahead and place that into our equation. So each of these are x, and the bottom one is 0.0250 minus x, and that is what we're left with here. So we can simplify this a bit. Write it as x squared divided by 0.0250 minus x. All right. We can ask the question of ourselves whether or not we can do an approximation. So meaning, can we say 0.0250 minus x is just approximated by 0.0250? Can we do that? So let's test that. What is Kc multiplied by 100? That gives us a value of 19.0. And we see that that is in fact much larger than 0.0250. So therefore, we cannot approximate. All right, because it's going to be, this x value is significant. It's a significant value that we want to subtract from the concentration. So we have to leave it as is. We have to work with it as such. So let's solve this equation. I'm going to multiply this to the left here. And then, yeah, so let me write that out. 0.190 multiplied with 0.0250 minus x is equal to x squared, and that gives me a quadratic expression of x squared plus 0.190. So right, I just took the x, just putting everything to one side, minus 0.00475 is equal to 0. All right, so I expanded the brackets, and then I put everything on one side. So now to solve for x, we can use the quadratic formula, or if you have a fancy calculator, then you can use that. And we will use the quadratic formula in this case. So minus b plus minus b squared minus 4ac divided by 2a. All right. Remember, what is a? So a is the coefficient of the x squared. Sorry, there needs to be an x there. 0.190x. The b coefficient is what goes in front of the x. So the first power root, and then the c is our lone standing, is just our, what do you call these things again? I can't completely recall, but anyway, so then let's plug in. So you should get two values for, or two solutions for the roots. So that is x1 and x2. x1 I got as 0.0222 and some numbers, and x2 as minus 0.212. And remember, these should be molar quantities, and hence that means that this value is impossible. Right, because we can't have a negative concentration or a negative change in concentration. I mean, it just doesn't make sense. So because x, as we see here, it actually needs to be the concentration of the CO and the Br2 at equilibrium. So it cannot be a negative value, and hence it makes this our choice. All right, so it makes x1 our choice. So we can just go ahead and say, right, therefore the concentration of Br at equilibrium is just equal to x, and now we can round to the correct number of significant figures. All right, which is 3. So that's a 4, 2 to 4 molar, and of course the same goes for, let me actually write that here. So therefore the concentration of CO at equilibrium is equal to x, and rounds to the same value, 0.0224 molar. And then the concentration of COBr2 at equilibrium is of course equal to 0.0250 minus x, which we can round to 2.63 times 10 to the negative 3 molar. All right, so that's the first part of the question. The second part of the question said, what percentage of the original carbonyl bromide decomposes at this temperature? All right, and that essentially is just a percentage calculation. So it says percentage decomposed. So to calculate the percentage decomposed, so that would be the amount that reacted divided by the initial amount multiplied by 100%. So what we're interested in is the amount of COBr2, let's call it reacted, divided by the amount of COBr2 initially, and we want to multiply that by 100%. That makes sense, right? So the amount that actually was used up, reacted, the amount that decomposed, divided by the initial amount, multiplied by 100%. So the amount that is reacted is differently put. It's of course the initial amount minus the amount left over at equilibrium, right? So meaning it's the initial amount minus the amount left over. That would give us the amount that was reacted. And if you calculate that, then you should get a the value of actually of one of the products that formed. So that's about 0.0224 molar. And that's the amount that reacted. And that also makes sense because this is a 1-to-1-to-1 stoichiometry, so the amount of one product that produced should be the amount of one product that reacted. So the value that I got here, so I mean I can also just perhaps just write out one more step. It is divided by 0.0250 multiplied by 100%, and that gives a rounded value of 89.6%. So 89.6% of the original carbonyl bromide decomposed. And that's what the question asked, right? So what percentage of the original carbonyl bromide decomposed at this temperature? And that's 89.6% of it decomposed. All right. Cool. So this was a typical equilibrium question, and we connected a bit to decomposition, because decomposition basically just means when you have one reactant and it breaks down into the components that it consists of. You can see this thing consists of carbonyl and bromide, right? So they just split back into those two gases. Great. I'll just go back to that screen. Thank you for watching. I'll see you in the next video.